Hello and welcome back to Machine Learning. I'm Jivita Christie, and in this video, we are going to take a look at regularization, optimization, and hyperparameter tuning in neural networks. So let's begin. First, let's revise the concept of underfit, overfit, and goodfit, which we have already seen before. So underfit, a model that is underfit is a model that fails to sufficiently learn the problem and it performs poorly on a training data set and does not perform well on a holdout sample. So that means an underfit model is a model that not only performs poorly on the training data set, but also performs poorly on the test data set because it has not been able to sufficiently learn the problem from the training provided. Just like we have an underfit model, we could also have an overfit model that learns the training data set so well that it performs very well on the training data set, but does not perform well on the holdout sample. So an overfit model is the one that gets trained so well and learns so well that it performs very well with the training data set and gives you great accuracy with it, but does not give you a good performance with the test dataset. And finally, we have a good fit model, which is something that suitably learns from the training set and is able to generalize, and it's also able to perform well with the test dataset. Now let's talk about regularization. So strategies or techniques which are used to reduce the error on the test set at an expense of increased training error are collectively known as regularization. So basically, regularization is meant for overfit models because in overfit models, the model performs very well with training set. So what regularization does is it tries to increase the error when the model is working with a training set. This way, it's not going to be overfitted, and that way it can work better with the test data set. So such techniques are known as regularization techniques. You can define them as any modification we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. Okay, so this is actually the definition of overfitting. So if this happens, you're able to reduce the generalization error, but not the training error. That means your training error is going to increase, but not the generalization error. So then you can say that you're performing regularization. Now, regularization is often done by putting some extra constraints on a machine learning model, such as adding restrictions on the parameter values, or by adding extra terms in the objective function that can be thought of as corresponding to a soft constraint on the parameter values. So most machine learning models have some or the other parameter, and neural networks have lots of parameters, so you could add some restrictions on those or add some extra functions, extra terms to your objective function in neural network, and you can perform regularization. And if you choose all these values correctly, then it can reduce your testing error. An effective regularizer is said to be the one that makes a profitable trade by reducing variance significantly while not overly increasing the bias. Okay, so bias is if bias is going to increase a lot, then it will lead to a problem. And if variance is increasing a lot, that also causes a problem. But there is something called a bias variance trade-off in machine learning, which deals with striking the perfect balance of bias and variance. Because bias and variance are completely opposite. If you increase bias, variance will decrease. If you decrease bias, variance will increase. But both of them are bad for a machine learning model. So you need to have a model that's going to have, just the right amount of bias and variance. Now let's talk about some methods that we have for implementing regularization for neural networks. So the first one is the weight regularization, also known as weight decay. Here you penalize the model during training based on the magnitude of the weights. Okay, so we know that from every layer to another layer, but for all the neurons there are weights. So if you can penalize the model based on those weights at every iteration, then you could perform regularization. So this will encourage the model to map the inputs to the outputs of the training data set in such a way that the weights of the model are kept small. And this is also known as weight regularization or weight decay, and it has proven very effective for decades for both simpler linear models as well as neural networks. The next method is activity regularization, where you penalize the model during the training phase on during training based on the magnitude of the activations. So we know that uh, every neural network also has certain activation functions for each layer. And if you take their magnitude and penalize the model based on that, then also you could perform regularization. And such a regularization is known as activity regularization. Next, we have the weight constraint. So if you constrain the magnitude of weights to be within a range or below a limit, then also you could perform regularization. The next method is dropout, where you probabilistically remove inputs during training. Okay, so you try to remove certain inputs from the training set during the training phase so that the model does not overfit. Okay, remember we are trying to reduce the overfitting, and that's why we're doing all this. So it's possible that there are certain inputs in your data set that are causing this overfitting problem. So you could remove some such inputs during the training phase. Next, we have noise. So dropout and noise, they are both opposites of each other. In dropout, you try to remove some inputs. In noise, you try to add some statistical noise to the inputs so that the machine does not, conform to the training data set so much. Next, we have early stopping. So you will monitor the model's performance on a validation set, and then you will just stop training when the performance degrades. Okay. So you're not just going to train the model all the way, but you will just train it up to a point where you find that the performance is degrading. And that's why you're just going to keep on checking the model performance during the training phase using a validation dataset. The next method is dataset augmentation. So it's the best and easiest way to generalize a model is to train it on a large data, but most of the time we have limited data. And so to create a large data, you could create fake data. This can be done using, generative adversarial networks, which we studied earlier, or some other technique. And you could add this fake data to your data set, and that would just easily reduce the overfitting. The next method is bagging. So in bagging or bootstrap aggregating, you could reduce generalization error by combining several models. So if you remember, this is also known as ensemble, like random forest, which is an ensemble of several trees, decision trees. In the same way for neural networks as well, you could train several models and then use all of them through some type of a voting system. And then we have adversarial training. So in adversarial training, if the models are trained on training sets that are augmented with adversarial examples, it would improve the generalization of the model. So just as I said before, you could use generative adversarial networks to generate new data points and add them to your data set, and then use that to train your model. That could reduce overfitting. So now that we have talked extensively about about regularization, let's now talk about optimization. So in deep learning, we have the concept of loss. There is a loss function. which tells you how poorly the model is performing at that current instant. So we need to use this loss function to train our network in such a way that it would perform better. So what we need to do is to take the loss and then try to minimize it, because a lower loss would mean the model is going to perform better, right? So we have to use the minimization function to reduce the loss. And this process of minimizing, or in fact, even maximizing any mathematical expression, is known as optimization. And we could do that to neural networks as well. But here the goal is not to maximize, but to minimize the loss function. Optimizers are algorithms or methods used to change the attributes of the neural network, like weights and learning rate and other attributes, which could reduce the losses. Optimizers are used to solve optimization problems by minimizing the function. And let's take an example. So as a mental model, you could think of a hiker that is trying to get down a mountain with a blindfold on. Okay, so the hiker has a blindfold, and so the hiker cannot see, but he or she is trying to get down a mountain with a blindfold. So what happens? It's impossible in the beginning to know which direction to go in. But then what happens? One thing she can know, that she has to go downwards, right? She cannot move upwards. So your body, even though you cannot see, you can still feel a slope, right? You can see that you're moving downwards. So if you're moving, if you know that you have to move downwards, okay, you just don't know in which direction, then you could just find a way through trial and error method. And eventually she would just keep on taking steps downward and she'll reach the base of the mountain, right? So similarly, when you begin with your neural network, in the beginning, it's not necessary that you will be knowing the right weights from the start. Okay, but with some trial and error methods, you could you could end up getting to that point eventually, such that your loss function is minimized. Okay, you get weights in such a way that the loss function is minimized. Now, remember, in case of a loss function also, you know that reducing its value is good and increasing is bad. So at least you know which direction you have to go in there. Okay, so you can adjust your weights accordingly. Okay, now how you should change your weight or learning rates of your neural network to reduce the losses, all that is defined by whatever optimizer you are using. And optimization algorithms are responsible for reducing the losses and to provide the most accurate results possible. Now, we're going to see a couple of algorithms that can be used for optimization. One such algorithm is the gradient descent algorithm. Okay, it is an optimization algorithm for finding a local minimum of a differentiable function, and it is used to find the values of a function's parameters, which are coefficients that can minimize a cost function as far as possible. In our case, these parameters are the weights associated with the neurons. The next algorithm is known as stochastic gradient descent, also known as SGD, which is an extension of the gradient descent algorithm, and it helps in overcoming some of the disadvantages of the gradient descent algorithm. So one of its disadvantages of that means of gradient descent is that it requires a lot of memory to load the entire data set of endpoints at a time to compute the derivative of the loss function. And you have to keep on doing this over and over. So every time you have to load this big data set, and that's why it requires a lot of memory. In the SGD algorithm, the derivative is computed taking one point at a time. So you're not computing derivative of the entire endpoints, but you're taking one point at a time and calculating the derivative. So that's the difference between the gradient descent and the stochastic gradient descent algorithm. Now let's talk about hyperparameters. Okay, so what are hyperparameters in terms of neural networks? So in a neural network, any parameter that you can tune or you can change or adjust to make the model perform better would be a hyperparameter. And such are batch size and training epochs. So batch size is how much of the data that you have is going to pass through the model through one layer at a time. And the training epochs are how many iterations you're going to run your neural network for to train your model. And then we have an optimization algorithm, which would help you to optimize all these values. So that is again a hyperparameter. You can optimize the learning rate and momentum at which the model is working. You can also adjust the network weight initialization. Obviously, weights will get adjusted later on, but it also matters what kind of initial weights you're choosing. And there's also activation functions, which are there in the hidden layer. Those functions also can be tuned. You could also tune out dropout regularization, okay, deciding which kinds of inputs should be removed from the data set. And you could decide how many number of neurons are there in the hidden layers. So there are all these parameters that you can take care of to make your model work better. And that is known as hyperparameter tuning, deciding what values will be there for all these parameters. And to do this, we have several methods. One such method is hand tuning, which is also trial and error. So here you're not going to use any particular mathematical method, statistical method, or anything like that, a program. You're just going to hand tune these parameters, which means you yourself are going to run several experiments and choose different parameters every time and see which one works the best. Next, we have grid search. So here you create a grid based on all the parameter values, and then all possible parameter combinations are tried, and then the best one is selected. So this is more like a dynamic programming algorithm where you create a table, try out all possibilities, and pick the best one. Then we have random search. So here, instead of trying all possible combinations like we did in a grid search, only a randomly selected subset of the parameters is tried, and from that subset, whatever works the best is selected. Then we have the Bayesian optimization, also known as the Gaussian process, which uses a set of previously evaluated parameters and resulting accuracy to make an assumption about unobserved parameters. Okay, and in this, some acquisition function is used, which suggests what should be the next set of parameters. And finally, we have the tree-structured Parson estimators, where in each iteration, this algorithm collects a new observation, and at the end of the iteration, it decides which set of parameters should be tried next. Okay, so both Bayesian optimization and tree-structured Parson estimators, both of them are using some technique to first analyze one set of parameters and then decide what should be the next set based on how the current set of parameters performed. Okay, so, and of course, both these techniques are very statistical techniques with a lot of algorithms. So it's nothing like hand tuning where you are trying to tune the model yourself. But you have all these techniques available for hyperparameter tuning for your neural network. So I hope you understood all this, and I'll be back with the next video. So I'll see you there, and thank you for watching.